Back from the break, we're looking at some basic circuits, in particular the XOR gate. The XOR gate has many uses, as you're probably well aware. Unlike the NAND gate, it's not quite as straightforward to implement, but it's also not that difficult. We're going to look at two versions of an XOR gate. One is a passive structure, and one is an active structure. There's lots of disadvantages with the passive structure, and less so with the active structure. The active structure is created in full CMOS. It makes response times faster. But it does use more transistors in the design. But I think nowadays people really don't care about the number of transistors that are being used in an implementation, because it really makes very little difference on a very large scale design, and you'd rather have a more robust design than something which has squeaked out a minimum number of transistors but has considerable disadvantages. But anyway, we'll take a look at it just to get familiar with some layout and a schematic of a passive XOR gate. Of course, it is quite a clever circuit, and over here is sort of shown the transistor level schematic with N and P type transistors, and here's a representation of a layout. And one of the things to think about while we're going through this is, why it's not such a good design. So you can look at a couple different scenarios. Typically you put, basically we're going to do a logic simulation on this, so we're going to put logic 0 on A and a logic 0 on B and sort of see what happens. So we just sketch out on the figure what the different colors represent the different logic values. And you'll see once we have that scenario that this thing in the middle here is a transmission gate. So it's good for passing both highs and lows when it's on. This here you recognize as obviously an inverter. So in this particular case, what we're going to end up doing is connecting the output to the input B, and we'll, if you looked at the truth table, that would be the correct logic for that particular gate. Again, you can go through it with different values on A and B. In this case, A is equal to 0, B is equal to 1. And again, then the circuit represents with different colors which levels are at different values. And we can see again what's going to happen in this particular case. That transmission gate is going to be on, and we're going to be driving again the output from the B input, which in this time happens to be 1. So we can do the same thing for A equals 1 and B equals 0, and basically walk through the design again. A notable difference here is that our transmission gate is off, and then we might ask ourselves which transistor is pulling V out up. And in this particular case, we'll see that since B was equal to 0, this PMOS transistor up here is going to be on, and it's going to be pulling V out to A. The last scenario to look at, since it's only two inputs, is the case where A and B are both equal to 1. And again, we'll go through the diagram and sort of see what's on and what's off. That transmission gate is off, and we might ask ourselves again which transistor or transistors are pulling V out down. And in this particular case, we'll see that it's V out is pulled down actually to ground through the transistors associated with the gate. So that's that N-type transistor that's on, and that N-type transistor that's on. So in most of those cases we looked at, you could ask yourself, where did the drive come from? And I think it's only this latter case you'll see that it came from actually VDD or ground. This is sort of what a nicely compacted layout might look like. It certainly does look like it's been optimized. It's kind of difficult to sort of identify individual components or parts of the structure, but if you sort of reverse engineered it, certainly when you have the transistor level schematic near you, you should be able to probably figure out what's what. It would be difficult to reverse engineer, but there are companies that actually make their money reverse engineering much more complicated circuits than this in a fabrication technology, where they have to sort of burrow through each level and try to find out how something was connected up. This is an active XOR gate. As you can see, it's slightly more complicated. Certainly anyone here could probably come up with this, maybe not at first blush, but when you break it into the components there, you'll see that you probably would be able to without much difficulty. So again, we can look at scenarios with A is equal to 0, B is equal to 0, and verify that the output is equal to 0. And again, we just sort of go through the circuit and see what lines are tied to what values and the consequences of that. So in this particular case, since these are all zeros, these are N-type pull-down structure, this guy's going to be off and out of the picture. And then some of the devices that are going to be on are going to be these two here, because they're both at a logic low coming in. So there's going to be a conducting path from VDD to this output here. So what that'll do is go through this inverter and invert it. So we got the behavior that we'd expected. Again, we can go through other values for a equals 0, b equal 1, sort of see what happens, and look for in this particular case it's being pulled down, and now it's being pulled down but through this n-type transistor and this n-type transistor, because the inputs on both of these are equal to 1, or a logic 1, maybe 5 volts or 3 volts. So in that case, again, we get the right logic value. And again, you can look through other examples, set up different values of input and output, and certainly you should be able to analyze a circuit of this this complexity within, I wouldn't say in your head, but on a piece of paper for sure. And you'll sort of see that the values are what they should be. This time it is sort of indicated that it's being pulled up through this p-type transistor, which is on, and that's why that blue line is slightly shifted over a bit. And this guy here, since it's got a 0 on the input, this n-type transistor is off, isolating the pull-down section from the pull-up section. A couple things to note. This thing out here looks familiar. It's our friend. It's our NAND gate, a NAND kind of structure. And this here looks like a slightly more complicated gate, but the important thing to note is that in the pull-down section, it's the dual of the transistors in the pull-up section. So these two down here were in parallel. These two up here that correspond to them are in series. These guys here are in parallel. These down here are in series, as we expect with all our static NAND type of gates. Here's the layout. It looks considerably more larger. Perhaps not that much more complicated, but it's larger, maybe more difficult to sort of figure out what's connected to what, but certainly could be done. And you can ask yourself, like, how else would you be able to implement this? And I sort of ask you to provide a gate level implementation of your design and use NAND gates only. You probably are aware that you can build any circuit you like out of NAND gates, so the exercise is to sort of build an active XOR gate. This is just the schematic representation that corresponded to that layout, and there are a couple things that you can probably recognize. Certainly we're aware of some with this NAND gate, this kind of complicated logic function in this inverter, and it's relatively straightforward to see the inverter on the output here. So we have P6 and N6 transistors which are tied together, and they represent the inverter on the output. And it happens to be laid out in a fashion where it was relatively easy to identify. So it used 12 transistors, better performance at the cost of a little more hardware, but nowadays that's probably a don't care. The first section we recognize is that NAND gate. The middle section implemented that logic function if we were to work it out with not much difficulty. And the last section was an inverter. So the nice thing about it is it asserts a stronger output than the passive XOR. You can cascade these together without worrying about drive coming from the gate before it. In a lot of cases you end up cascading XOR gates. At this point in time we'll take a brief break. There's a few things to think about there, but not overly complicated.